Hi, my name is Maren and I'm going to be talking about section 7.4 partial fractions. Before I get started and get into the meat and the nitty-gritty of it, I wanted to talk about the purpose of why we're learning partial fractions. There's two big reasons that I can see. The first is growth mindset. It's teaching us to encounter a challenge and to solve it and to be able to have that sense of accomplishment and also know that we have that problem-solving skill set. If we feel frustration when we see a problem like this, we can't let that frustration stop us. We just have to think, I guess I just haven't learned this yet, and see it as a learning opportunity. The second is when we have a problem like this is something that comes from biology. It's an example from our textbook. And biologists determined a way of using less pesticides when growing a crop. And so they would introduce these sterile flies to these females and then be able to slowly decrease that population so that those crops wouldn't get ruined. So we have here T equals time, P equals the number of females, S equals the number of males. We're not going to solve this problem today, but this is an example of why we would use partial fractions in order to help better the world. So I thought that was pretty neat. But let's take a look at a little bit simpler one with x's and numbers, something that we'll be able to solve in a fairly straightforward manner. So we're going to look at an indefinite integral, and we have here x plus 5 over x squared plus x minus 2. Don't forget the dx. So I look at this function, and the first thing I'm going to do is think about the integration techniques that I already know. The first one I think of is u sub. If I wanted to use u substitution for this function in order to integrate this, I would probably choose x squared plus x minus 2. And then I would get du to be 2x plus 1 dx. There is no 2x plus 1 in the numerator, so it falls apart. We can't use that one. So, what's another one of our integration techniques? We've also learned integration by parts. So for that one, as you recall, we've got a u, we've got a dv, we need to find the derivative of u, and we have to find the antiderivative of dv. Either one of these, we're going to have to find the derivative or the antiderivative of it, and that's going to get messy and complicated. So if I choose x plus 5 to be my numerator, I'm going to get dx, and if I choose 1 over x squared plus x minus 2, we kind of run into the same situation that we had before, where we have a v and it's just not going to work as cleanly. So we're going to cross that method off. The third method we know is trig integrals. That one is pretty obvious why that one won't work, because there is no sine or cosine or cotan or cosecant, any of those guys. The last one is trig substitution. So for that one, typically some sort of perfect square. We don't have that. We have a quadratic function here on the bottom. But what I do see right away when I look at that, I think back to my 7th, 8th grade algebra, something around that, probably my middle school days, painful days. And I recall factoring. So I can look at this denominator here, and I can look at it in a simpler manner by expanding it. So I'm going to go ahead and do that. So I'm just going to focus on the denominator. I have two terms. I've got x plus 2 and x minus 1. I've got x plus 5 on the top, but we're just going to leave that blank for now. So I also know from my understanding of fractions that I can separate this into two different fractions. So this then becomes a fraction, or a numerator on top that we don't know yet, over x plus 2 plus a numerator that we don't know yet over x minus 1. And we don't know what that is because we have to divide out our numerator first. But we don't know how it is going to be divided out so that it equals this x plus 5. So let's go ahead and figure out how to do that. So I'm just going to erase this. And instead of boxes like we had, I'm going to use letters. And it's not equal to, so I'm just using an arrow to signify that it doesn't equal, but we're moving on to the next step. So instead of x plus 5, I'm going to do, or instead of a box, I'm going to have a over x plus 2 plus b over x minus 1. And I chose the a with the x plus 2 because when I factored it, I saw that my middle one here meant that the larger number would be positive, and so I just put the positive and the bigger number first, just kind of, that's an easier way for me to think about it and organize as I solve the problem. So now what I need to do is get my least common denominator. So I'm going to multiply the original function by both of those, or I can just multiply x minus 1 times x plus 2 on both sides. Either way is going to work. So now I have my numerator, my original numerator, x plus 5 equals a, the x plus 2's will cancel, times x minus 1 plus b, my x minus 1's will cancel, times x plus 2. And we could set up a system of equations, or what we could do is try to eliminate one side of it to get it to 0. So, for example, if x equals 1, 1 minus 1 is 0, 0 times a, that a goes away. Then we can solve for what our b would be. So, if this x is 1 plus 5, that goes away. B times x, oops, 1. So I've got 6 equals b times 3, divide by 3, da 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 da, b equals 2. Now let's, I'm actually going to show you the system of equations so that you can see that too. We could do the same thing for x equals -2 and then eliminate the b so we get the a term, but I want you to also see the system of equations method. So we're just going to keep b equals 2 over here so we don't have to figure that out either. So all I'm going to do is distribute my terms. So I have ax minus a plus bx plus 2b, and I'm going to combine like terms. So we have x plus 5 equals x times, and I also like to cross them off as I go. So I have ax, and then I have bx. So I have a plus b, and then I have minus a plus 2b. And then I match them up. So if we had more terms here, let's say if we had x cubed plus x squared, whatever is in the inside, we're going to set it equal to the coefficient in front of that corresponding term. So here I have an x to the 1 power, and inside I have a plus b. So we can imagine that there's a 1 here, for example. So a plus b is going to equal 1. And then 5 is going to equal negative a plus 2b. Since we already found our b, 2, it's not the best 2, but it's a 2, we've got a plus 2 equals 1, and I solve that, and I get a equals negative 1. So, I'm going to erase this, remember it. I'm going to go back. So my a is negative 1, my b is 2. Now I'm going to solve this integral with these new simpler fractions to solve and the a and b that I solved for. So like I said, we have an integral. We have the integral of negative 1 over x plus 2 plus 2 over x minus 1 dx. And now if you think back to our original integral rules and laws, you recall that when we have addition in between those two terms, we can divide that into two different integrals and think about it in that way. So I'm just going to put an integral sign there and a dx here. That just makes it a little bit easier for our brain to solve, and then we can combine those together at the end for our super integral. So I look at this and I see 1x on the bottom, and I could do a u substitution for it, so that I have 1 over u, and I'll do that for the first one. So we have u equals x plus 2 and du equals dx. So then we have the integral from negative 1 over u du. I know because I memorized my simple integrals that is going to equal negative ln absolute value of u plus c. But since the u, we're going to plug in our original term from what our u was. So then we have negative ln absolute value of x plus 2. I'm going to save that c for later. I'm just going to add it in when we solve for this one. So since we know that if we plug in our u substitution with that term, since it's just an x to the 1 power, we're just going to know straight away that that's going to be ln. So for this one, I'm just going to automatically think in my head, this is going to be 2 ln absolute value of x minus 1 plus c. So combining those two together, we have negative ln x plus 2 plus 2 ln x minus 1 plus c. I also want to look at my ln's and the inside of my ln's. Could these be simplified further? No, they could not. So this is my final answer. Now this type of partial fraction would be distinct linear factors. We see when we distributed it out, we had two distinct linear factors. You can tell it's linear because it makes a line. X to the 1 power. If we had x squared or x cubed, we would have either reducible quadratic factors or irreducible quadratic factors. So we would need to solve for ax plus b, cx plus d, or c, d, so on and so forth. But for now, we just started with the simple method.